Right now, as you listen to this, there is gold flowing through your bloodstream. Not much, just traces, a few milligrams dissolved in your tissues. But every single atom of that gold, every last one, was created in a cataclysm so violent that it briefly outshone an entire galaxy. 2 dead stars, each one packing more mass than our sun into a ball the size of a city, spiraled toward each other across millions of years, drawing ever closer, until they finally collided at a third of the speed of light. The impact released more energy in a single second than our sun will produce in its entire 10 billion year lifetime. And in that unimaginable violence, in that blinding flash of destruction, gold was born. So was platinum, so was uranium. So were dozens of other elements that you carry in your body right now, elements that make up the phone or the computer you are watching this on, elements that form the ground beneath your feet and the air in your lungs. You have probably heard the phrase, "We are stardust." And that is true. But the full story is so much stranger, so much more dramatic, and so much more beautiful than that simple sentence can convey. Because the elements that make up everything you have ever touched, everything you have ever seen, everything you have ever loved, they were not all made in the same place, or at the same time, or by the same process. Some were forged in the first 3 minutes after the Big Bang itself. Others were cooked slowly over billions of years in the bellies of ordinary stars like our sun. Still, others required the most extreme conditions the universe can produce, the crushing cores of stars 20 times more massive than our own, temperatures of billions of degrees, pressures that defy comprehension. And some elements, the heaviest and rarest, needed events so catastrophic that they happen only a handful of times per galaxy, per million years. This is the story of cosmic nucleosynthesis, the story of how every element on the periodic table came to exist. It is a story that stretches from the first heartbeat of the universe to the death throes of the most massive stars. It is a story of brilliant physicists who pieced together one of the greatest puzzles in all of science, sometimes against tremendous odds. And it is, ultimately, a story about you. Because you are not merely in the universe, you are made of the universe. And this is how you were assembled. Let us begin at the very beginning, not the beginning of the Earth, the Sun, or even our galaxy. The beginning of everything. Roughly 13.8 billion years ago, the universe erupted into existence from a state so hot and so dense that the laws of physics, as we understand them, simply break down. In the first fraction of a second, temperatures exceeded 1 trillion degrees. At these energies, matter as we know it could not exist. There were no atoms, no nuclei, not even stable protons or neutrons. Instead, the universe was filled with a screaming hot plasma of quarks and gluons, the fundamental building blocks of matter, all smashing into each other at nearly the speed of light. But the universe was expanding, and as it expanded, it cooled. By the time the universe was about 1/millionth of a second old, the temperature had dropped enough for quarks to bind together into protons and neutrons. Protons, each carrying a single positive charge, are simply hydrogen nuclei, the simplest atomic nucleus possible. Neutrons, carrying no electrical charge, are slightly heavier than protons, and when left alone, are unstable. A free neutron will decay into a proton, an electron, and a ghostly particle called an antineutrino in roughly 10 minutes. This simple fact, the instability of the free neutron, would have enormous consequences for the chemical composition of the entire universe. By about 1 second after the Big Bang, the universe had cooled to roughly 10 billion degrees. At this temperature, neutrinos, those nearly massless phantom particles that barely interact with anything, decoupled from the rest of matter and began streaming freely through space. They are still traveling today, forming an invisible cosmic background that permeates the universe, though we have never managed to detect it directly. Around this same time, electrons and their antimatter counterparts, positrons, were furiously annihilating each other. A very slight excess of electrons over positrons meant that, when the annihilation was complete, a small residue of electrons survived. These would eventually pair up with nuclei to form atoms, hundreds of thousands of years later. But first, the universe had some cooking to do. By about 1 minute after the Big Bang, temperatures had fallen to around 1 billion degrees. Still unimaginably hot by earthly standards, but cool enough for nuclear reactions to begin sticking. This is the era of Big Bang nucleosynthesis, and it lasted only about 20 minutes. That is all the time the universe had to build elements before expansion and cooling shut the nuclear kitchen down. The process started with deuterium. A proton and a neutron collided and fused together to form a deuterium nucleus, the heavy isotope of hydrogen. Deuterium is fragile, and at the temperatures present during Big Bang nucleosynthesis, most of it was immediately blasted apart by high-energy photons. But as the universe continued to cool, more deuterium survived. And once you have deuterium, you can start building heavier things. 2 deuterium nuclei could fuse to form helium-3, an isotope of helium with 2 protons and 1 neutron. Deuterium could also fuse with a neutron to form tritium, hydrogen with 1 proton and 2 neutrons. And from there, through a series of rapid collisions and fusions, the universe built helium-4, the common isotope of helium, with 2 protons and 2 neutrons. Helium-4 is an exceptionally stable nucleus. Its binding energy is high, which means once you make it, it is very difficult to break apart. This stability is both a blessing and a curse. A blessing because it meant the universe could efficiently produce helium. A curse because it meant helium was extraordinarily reluctant to fuse into anything heavier. And here, the universe ran into a wall. There is no stable nucleus with 5 nucleons. There is no stable nucleus with 8 nucleons. This is the so-called mass 5 and mass 8 bottleneck, and it is one of the most consequential facts in the history of the cosmos. If you smash a helium-4 into a proton, you get lithium-5, which falls apart almost instantly. If you smash 2 helium-4 nuclei together, you get beryllium-8, which is so unstable it disintegrates in less than 1/10 of a quadrillionth of a second. There simply was no efficient pathway from helium to carbon or oxygen, or anything heavier during Big Bang nucleosynthesis. A tiny amount of lithium-7 was produced through a roundabout chain of reactions involving beryllium-7, and even tinier amounts of other light isotopes appeared. But that was it. About 20 minutes after the Big Bang, the universe had cooled and thinned too much for nuclear reactions to continue. The primordial kitchen was closed, and so the universe settled into its primordial chemical composition, roughly 75% hydrogen by mass, 25% helium, with mere traces of deuterium, helium-3, and lithium-7. No carbon, no oxygen, no nitrogen, no iron, no gold, no silicon, nothing from which a planet could be built or a living thing assembled. The universe was, in chemical terms, extraordinarily boring. it would remain that way for a very long time. After the primordial kitchen closed, the universe entered what cosmologists call the Dark Ages. There were no stars, no galaxies, no light sources of any kind. The cosmos was a vast, expanding fog of hydrogen and helium, completely dark except for the fading glow of the cosmic microwave background radiation, which was itself rapidly redshifting out of the visible spectrum. If you had stood in this universe, you would have seen nothing. Absolutely nothing. Just blackness in every direction, stretching to infinity. This darkness lasted for roughly 100 to 200 million years. During that time, the only thing happening was gravity, working silently and patiently in the dark. Tiny fluctuations in the density of the primordial gas, fluctuations that had been imprinted during the earliest moments of the Big Bang and frozen into the cosmic microwave background, began to grow. Regions of slightly higher density attracted more gas from their surroundings, growing denser still. Over millions of years, these overdensities grew into vast clouds of hydrogen and helium, stretching across tens or hundreds of light years. Within these clouds, smaller clumps began to form. Gravity pulled the gas inward, compressing it, heating it. As each clump contracted, the gas at its center grew hotter and denser. Eventually, after millions of years of slow gravitational collapse, the temperature at the center of one of these collapsing clumps reached about 10 million degrees. At that temperature, hydrogen nuclei begin to fuse. The first star in the universe ignited. We have never observed a first-generation star directly. They lived fast and died young, and none are believed to survive to the present day. But theoretical models and increasingly powerful computer simulations tell us a great deal about what they were like. They would have burned with a surface temperature far hotter than our sun, emitting fierce ultraviolet radiation that ionized the hydrogen gas around them, carving out expanding bubbles of hot, glowing plasma in the otherwise dark universe. These bubbles grew and eventually merged, gradually reionizing the entire universe in a process that cosmologists call the epoch of reionization, which was essentially complete by about 1 billion years after the Big Bang. The deaths of population 3 stars would have been equally dramatic. The most massive of them, those exceeding roughly 140 solar masses, are believed to have died as parent stability supernovae. In these extraordinary explosions, the core of the star becomes so hot that the gamma rays produced in its interior have enough energy to spontaneously create pairs of electrons and positrons. This process removes pressure support from the core, triggering a catastrophic collapse. But unlike an ordinary core collapse supernova, the collapse ignites explosive thermonuclear burning of oxygen and silicon that completely disrupts the star, leaving no remnant behind. A parent stability supernova would have been among the most luminous events in the early universe, and it would have scattered tens of solar masses of heavy elements, including large quantities of iron, silicon, and oxygen, into the surrounding intergalactic medium. These first explosions began the chemical enrichment of the universe. The heavy elements they produced mixed with the surrounding pristine gas, and the next generation of stars formed from this slightly enriched material. Each successive generation of stars further enriched the gas, building up the cosmic inventory of heavy elements over billions of years. Astronomers trace this enrichment by measuring the metallicity of stars, a term that in astronomy refers to the abundance of all elements heavier than helium. regardless of whether they are actually metals in the chemical sense. The oldest stars in the Milky Way have metallicities less than 1,000th of the Sun's, while the youngest have metallicities equal to or even exceeding solar values. But to understand how stars enrich the universe, we need to understand exactly what happens inside them, what nuclear reactions turn simple hydrogen into every other element. The answer begins with the simplest process of all: hydrogen fusion. Hydrogen was being transformed into helium through nuclear fusion, and the details of how this works are worth understanding, because it is the foundation upon which all stellar nucleosynthesis is built. In stars with masses comparable to our Sun or smaller, hydrogen fusion proceeds through what is called the proton-proton chain. This is a beautifully simple series of reactions. Two protons collide, and in an extraordinarily rare event, one of them undergoes a transformation. Through the weak nuclear force, one proton converts into a neutron, emitting a positron and a neutrino. The resulting proton-neutron pair is a deuterium nucleus. This first step is agonizingly slow. An individual proton in the core of the Sun waits, on average, about 9 billion years before it successfully fuses with another proton. The Sun gets away with producing so much energy only because there is an incomprehensibly large number of protons in its core, all trying simultaneously. Once deuterium is formed, things speed up dramatically. The deuterium nucleus quickly captures another proton to become helium-3. Then, two helium-3 nuclei collide, producing a single helium-4 nucleus and releasing two spare protons back into the mix. The net result: 4 protons have been converted into one helium-4 nucleus, 2 positrons, and 2 neutrinos. And crucially, the helium-4 nucleus is slightly lighter than the 4 protons that went into making it. That missing mass, about 0.7% of the original, has been converted into energy according to Einstein's famous equation. This is the energy that makes the Sun shine. This is the energy that keeps a star from collapsing under its own gravity. This is the energy that has sustained life on Earth for billions of years. In our Sun, about 99% of the energy comes from the proton-proton chain. But in more massive stars, where core temperatures exceed about 17 million degrees, a different and faster pathway takes over: the CNO cycle. CNO stands for carbon, nitrogen, and oxygen because these elements act as catalysts in the reaction. The star does not consume carbon, nitrogen, or oxygen. Instead, it uses them as a kind of nuclear assembly line to convert 4 protons into helium more efficiently. A carbon-12 nucleus absorbs a proton, becoming nitrogen-13. The nitrogen-13 undergoes radioactive decay, spitting out a positron and a neutrino to become carbon-13. Carbon-13 absorbs another proton, becoming nitrogen-14. Nitrogen-14 absorbs yet another proton, becoming oxygen-15. Oxygen-15 decays into nitrogen-15, emitting another positron and a neutrino. And finally, nitrogen-15 absorbs one last proton and releases a helium-4 nucleus, leaving behind the original carbon-12 nucleus, ready to start the whole cycle again. The end result is the same. 4 hydrogen nuclei become one helium nucleus, and mass is converted to energy. But the CNO cycle is far more temperature sensitive than the proton-proton chain. A small increase in temperature produces an enormous increase in the reaction rate. This is why massive stars burn so much brighter and hotter than our sun, and why they exhaust their hydrogen fuel so much faster. Our sun will burn hydrogen in its core for roughly 10 billion years. A star 10 times more massive will burn through its hydrogen in perhaps 20 million years. A star 50 times the mass of the sun might exhaust its core hydrogen in just a few million years. But what happens when the hydrogen runs out? This is where the story takes a dramatic turn. When the core of a star has converted all of its hydrogen to helium, it can no longer generate the outward pressure needed to support the immense weight of the star's outer layers. The core begins to contract under gravity, and as it contracts, it heats up. The surrounding shell of hydrogen, now closer to the heat of the contracting core, begins fusing hydrogen at an accelerated rate. The extra energy puffs the outer layers of the star outward, and the star swells enormously. A star like our sun will expand to engulf the orbits of Mercury, Venus, and possibly Earth. Its surface cools as it expands, turning from yellow-white to a deep red. The star has become a red giant, but the core keeps contracting and heating. And eventually, in a star with sufficient mass, the core temperature reaches approximately 100 million degrees. At this temperature, something extraordinary becomes possible. Helium can begin to fuse. For stars with masses below about 2 solar masses, the ignition of helium is not a gentle affair. It is a bomb. The core of these lower-mass red giants has become so compressed that it is supported by electron degeneracy pressure, the same quantum mechanical force that supports white dwarfs. But degeneracy pressure has a peculiar property. It does not respond to temperature. In a normal gas, if you heat it up, it expands and cools, providing a natural thermostat. But degenerate matter does not expand when heated. It just gets hotter. And so when helium first begins to fuse in the degenerate core of a low-mass red giant, the energy released does not cause the core to expand and cool. Instead, the temperature rises, which accelerates the helium fusion rate, which produces more energy, which raises the temperature further. It is a runaway thermonuclear explosion deep inside the star, an event called the helium flash. In a matter of seconds, the core releases energy at a rate comparable to the luminosity of the entire Milky Way galaxy. It is one of the most powerful explosions that occurs inside stars, and yet you would never know it from looking at the star's surface. All of that energy is absorbed by the overlying layers of the star, and the only visible effect is a gradual readjustment of the star's structure over the following millions of years. After the helium flash, the core expands, the degeneracy is lifted, and helium burning proceeds steadily, fusing helium into carbon and oxygen through the triple alpha process. In more massive stars, above about 2 solar masses, helium ignition occurs before the core becomes degenerate, and the process is smoother and less dramatic. But the end result is the same. Carbon and oxygen are being manufactured in the hearts of stars. This is the triple alpha process, and it is one of the most remarkable reactions in all of physics. It is the gateway through which the universe builds everything heavier than helium. Without it, the cosmos would contain nothing but hydrogen and helium forever. No carbon, no life, nothing complex at all. The problem, as we discussed earlier, is the massate bottleneck. When 2 helium-4 nuclei collide, they form berylliumate, which is staggeringly unstable. It falls apart in about 1/10 of a femtosecond. That is 1/10 of a millionth of a billionth of a second. There is simply no time for a third helium nucleus to come along and join the party. At least, not under normal circumstances. But in the core of a red giant, conditions are anything but normal. The temperature is 100 million degrees. The density is enormous, with hundreds of thousands of grams packed into every cubic centimeter. Under these extreme conditions, even though berylliumate disintegrates almost instantly, enough of it exists at any given moment to create a tiny but steady population of berylliumate nuclei. It is a vanishingly thin window, but it is enough. A third helium nucleus smashes into one of these fleeting berylliumate nuclei and creates an excited state of carbon-12. Now, this excited state almost always falls apart again, decaying right back into 3 helium nuclei. It does this roughly 2,400 times out of every 2,401 attempts. But once, just once in about 2,401 tries, the excited carbon nucleus releases its extra energy as radiation and settles into a stable ground state. And just like that, carbon has been made. This process would be impossibly slow if it were not for a coincidence so precise, so seemingly fine-tuned, that it borders on the unbelievable. The excited state of carbon-12 that the berylliumate and helium-4 form happens to have an energy level that almost exactly matches the combined energy of a berylliumate nucleus and a helium-4 nucleus at the temperatures found in red giant cores. This is what physicists call a nuclear resonance, and it amplifies the reaction rate by a factor of millions. Without this resonance, the triple alpha process would be so slow that virtually no carbon would ever be produced in stars. This resonance was predicted in 1953 by British astrophysicist Fred Hoyle in one of the most audacious feats of scientific reasoning in history. Hoyle was a complicated man, stubborn and brilliant in equal measure, with a Yorkshire accent and a refusal to accept easy answers. He looked at the abundance of carbon in the universe, noted that the universe clearly had a lot of it, and worked backward. He reasoned that for carbon to be so abundant, there must be a resonance in the carbon-12 nucleus at an energy of about 7.65 million electron volts. If such a resonance did not exist, the triple alpha process would be far too slow to produce the observed amounts of carbon. It was a breathtaking piece of reasoning. Hoyle was using astrophysical observations, the simple fact that carbon exists in large quantities, to predict a property of the atomic nucleus that no experiment had yet measured. It was as if an archaeologist, studying the ruins of an ancient city, deduced the existence of a specific chemical compound in the city's construction materials before any chemist had ever synthesized it. The logic ran from the cosmos down to the subatomic. Hoyle traveled to the California Institute of Technology and told the nuclear physicists in William Fowler's laboratory that this resonance had to exist. They were skeptical, even dismissive. Why should they listen to an astrophysicist telling them about the properties of nuclei? That was their domain, not his. But a young physicist named Ward Whaling, intrigued by the boldness of the prediction, agreed to look for it using an old Van de Graaff particle accelerator that was not being used for anything else. Within a few months, the resonance was found, almost exactly where Hoyle had predicted. It was a stunning vindication, a case where astrophysical reasoning had successfully predicted a property of the atomic nucleus that experimentalists had not yet discovered. The result sent shockwaves through the physics community and immediately elevated both Hoyle's reputation and the credibility of the entire field of nuclear astrophysics. Once carbon is formed in the core of a red giant, additional reactions follow. Carbon can capture another helium-4 nucleus to become oxygen-16. Oxygen can capture another helium to become neon-20. The relative rates of these reactions, the competition between carbon production and carbon destruction, determine the ratio of carbon to oxygen that the star produces. And it turns out that the details of these rates are exquisitely sensitive to the properties of certain nuclear energy levels. If the resonance in oxygen-16 were just slightly different, stars would burn almost all their carbon into oxygen, and the universe would be carbon-poor. Life as we know it, built on the remarkable chemistry of carbon, might never have arisen. But the universe, through what appears to be either an astonishing coincidence or deep structural necessity, has arranged its nuclear physics just so. Carbon and oxygen are both produced in abundance. And from these two elements, the entire periodic table begins to grow. In stars below about 8 solar masses, the story of nucleosynthesis in the core essentially ends here. These stars never develop temperatures high enough to fuse carbon. Their cores contract. Their outer layers are gently expelled into space as beautiful planetary nebulae, and the remaining core settles into retirement as a white dwarf, a dense, slowly cooling ember composed mostly of carbon and oxygen. These white dwarfs are roughly the size of Earth, but contain the mass of the Sun. They are supported against further collapse by a quantum mechanical phenomenon called electron degeneracy pressure. But in more massive stars, the story is just beginning. When the helium in the core of a massive star is exhausted, the core contracts again, and the temperature rises even higher. At about 500 million degrees, carbon begins to fuse. Carbon-12 combines with carbon-12 in a violent reaction that produces a variety of products: sodium-23 and a proton, neon-20 and a helium nucleus, or magnesium-24 and a gamma ray. These reactions release energy, but less than the previous burning stages, and they proceed much faster. While hydrogen burning in a massive star might last millions of years, and helium burning several 100,000 years, carbon burning is over in a matter of centuries. The star is now in a race against time. Each successive fuel burns faster and faster, producing less and less energy, and the star is increasingly desperate to find new sources of support against its own crushing gravity. After carbon burning comes neon burning. This is a strange process. Rather than two neon nuclei fusing together, which would require temperatures too high even for this extreme environment, high-energy photons in the core blast neon-20 apart through a process called photodisintegration. The helium nucleus released in this breakup is then captured by another neon nucleus, building magnesium-24. Neon burning lasts only about a year. Then comes oxygen burning at temperatures around 2 billion degrees. Two oxygen-16 nuclei fuse to produce silicon-28 and a helium nucleus, or sulfur-31 and a neutron, or phosphorus-31 and a proton, among other products. Oxygen burning lasts perhaps 6 months, and finally, silicon burning. This is the last stage of nuclear fusion that a star will ever undergo. But silicon burning is not really burning in the traditional sense. At temperatures exceeding 3 billion degrees, the environment is so extreme that photons have enough energy to disintegrate silicon nuclei, breaking them apart into their constituent protons, neutrons, and helium nuclei. These fragments then recombine and rearrange. through a complex maze of thousands of nuclear reactions occurring simultaneously. In a state approaching what physicists call nuclear statistical equilibrium, the end product of this frenzied reshuffling is the most stable nucleus in all of nature, iron-56, along with its close neighbors nickel and cobalt. Silicon burning takes about a single day. One day, after millions of years of hydrogen burning, hundreds of thousands of years of helium burning, centuries of carbon burning, a year of neon burning, and months of oxygen burning. The final stage lasts just 24 hours. The acceleration is breathtaking. At this point, the star has developed a structure that astronomers often describe as resembling an onion. At the very center sits a core of iron, surrounded by a shell of silicon and sulfur, then a shell of oxygen, then neon, then carbon, then helium. And finally, on the outside, a vast envelope of hydrogen. Each shell is a different nuclear furnace, burning a different fuel, all nested one inside the other. And at the center of it all, the iron core grows. Iron is the end of the line for nuclear fusion. Of all the elements in the periodic table, iron-56 and its neighbor nickel-62 have the highest binding energy per nucleon. What this means, in practical terms, is that fusing iron into anything heavier does not release energy, it consumes it. Every nuclear reaction up to iron has released energy, providing the outward pressure that keeps the star from collapsing. But iron is the endpoint. It will not give up energy. It can only take. This is the iron catastrophe, and when it strikes fast. The iron core grows, fed by the silicon-burning shell above it, until it reaches a critical mass of roughly 1.4 solar masses. This is the Chandrasekhar limit, named after the brilliant Indian-American astrophysicist Subrahmanyan Chandrasekhar, who calculated it in the 1930s while traveling by steamship from India to England. He was just 19 years old at the time, a student heading to Cambridge to work with Sir Arthur Eddington, one of the greatest astronomers of the era. Chandrasekhar had worked out the mathematics of stellar structure during the long ocean voyage, and he arrived at the startling conclusion that there was a maximum mass above which a white dwarf could not support itself against gravitational collapse. Eddington publicly ridiculed the young student's result, a humiliation that Chandrasekhar bore with remarkable dignity. It took decades for the physics community to recognize that Chandrasekhar had been right all along. He was eventually awarded the Nobel Prize in Physics in 1983, the same year as William Fowler, for his theoretical work on stellar structure. Beyond the Chandrasekhar limit, the electron degeneracy pressure that has been supporting the core against gravity is overwhelmed, and in less than a second, the core collapses. The collapse is catastrophic. The inner core falls inward at speeds reaching 70,000 kilometers per second, nearly a quarter of the speed of light. As the core compresses, temperatures soar to over 100 billion degrees. The density exceeds that of an atomic nucleus. At these densities, protons and electrons are forced together through inverse beta decay, combining to form neutrons and neutrinos. The neutrinos, trillions upon trillions of them, burst outward from the collapsing core, carrying with them the vast majority of the gravitational energy released by the collapse. Roughly 99% of all the energy of the explosion is carried away by neutrinos, invisible to the eye, but devastating in their totality. The inner core collapses until it reaches nuclear density, roughly 250 trillion grams per cubic centimeter. At this point, the strong nuclear force resists any further compression. The core rebounds, like a rubber ball hitting a concrete floor, and this rebound sends a shockwave outward through the still-falling outer layers of the star. For decades, astrophysicists struggled to understand exactly how this shockwave becomes powerful enough to tear the star apart. In computer simulations, the shock would stall, losing energy as it fought through the dense material still raining down from above. It seemed like the explosion should have failed. The answer, still being refined today, appears to involve those neutrinos. Even though neutrinos barely interact with matter, the densities just above the newly formed neutron star are so extreme that a small fraction of the outgoing neutrinos deposit their energy into the material behind the stalled shock. This neutrino heating, combined with turbulent convection and fluid instabilities, revives the shock and drives it outward with enough force to blow the entire star apart. The star has become a supernova on February 23, 1987. This exact scenario played out in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way located about 168,000 light-years away. A blue supergiant star called Sangelik-69202 exploded, becoming supernova 1987A. The closest supernova observed since Kepler's supernova in 1604. For astronomers, it was the event of a lifetime. Many of them had spent their entire careers studying supernovae that occurred in distant galaxies, faint smudges of light that required the largest telescopes on Earth to observe. Now, suddenly, there was one in their cosmic backyard. And roughly 3 hours before the supernova became visible to the naked eye, a burst of neutrinos arrived at Earth. They passed through the entire planet without slowing down, but a handful of them, a precious few, interacted with the water molecules in underground detectors. Deep underground, in the Kamioka mine in Japan, a detector called Kamiokan-2 registered 11 neutrino events in a span of about 13 seconds. It was a vast tank of 3,000 tons of ultrapure water, ringed with roughly 1,000 photomultiplier tubes, waiting for the faint blue flashes of Cherenkov radiation produced when a neutrino, on exceedingly rare occasion, interacted with a water molecule. The detector had not been built to observe supernova neutrinos. It had been built to search for proton decay, a prediction of grand unified theories in particle physics. No proton decay was ever found, but when the data tapes were analyzed in the days after the supernova, a graduate student named Masayuki Nakahata noticed something in the recordings. The next morning, his colleague Keiko Hirata identified an unmistakable spike in the data, clearly distinct from the background noise. 11 events clustered together in a burst lasting roughly 13 seconds. It was the neutrino signature of a dying star. Simultaneously, the IMB detector beneath the shores of Lake Erie in Ohio detected 8 events, and the Baksan detector in the Caucasus Mountains of Russia caught 5 more, 24 neutrinos in total, arriving in a brief pulse from a dying star 168,000 light-years away. It does not sound like much. 24 particles from a star that released 10 to the 58th power of them. The detection efficiency was absurdly low. But those 24 neutrinos were enough. They confirmed decades of theoretical predictions about how massive stars die. They proved that the core collapse of a massive star releases an almost incomprehensible torrent of neutrinos, carrying roughly 3 times 10 to the 46 joules of energy. That is more energy than our sun will produce in its entire 10 billion year lifetime, released in a matter of seconds. The visible light of the supernova, spectacular as it was, represented less than 1% of the total energy. The neutrinos carried the rest, invisible messengers of catastrophe that passed through the Earth and everything on it, as though we were not even there. The detection of those neutrinos opened the field of neutrino astronomy. Before SN 1987A, the only confirmed extraterrestrial source of neutrinos was the Sun, whose steady stream of low-energy neutrinos had been detected since the 1960s. Now, for the first time, neutrinos have been observed from a cataclysmic astrophysical event outside our own galaxy. It was proof of concept that the universe could be studied not just with light, but with neutrinos, and eventually with gravitational waves as well. We live in the era of multi-messenger astronomy, and SN 1987A was where it began. For Masatoshi Kashiba, the leader of the Kamiokande experiment, this discovery would eventually earn the Nobel Prize in Physics in 2002. But more importantly for our story, the supernova confirmed something fundamental about how elements are made. When the shockwave tears through the layers of the dying star, it heats the material to extreme temperatures, triggering a wave of explosive nucleosynthesis. In the silicon and oxygen layers, new elements are forged in seconds. Radioactive nickel-56 is produced in abundance, and its subsequent decay through cobalt-56 to stable iron-56 powers the visible light of the supernova for weeks and months after the explosion. This was directly confirmed in supernova 1987A, where space-based gamma-ray telescopes detected the characteristic gamma rays of cobalt-56 decay, escaping from the expanding debris. Even now, decades later, the remnant of supernova 1987A continues to glow, currently powered by the decay of titanium-44, an isotope with a half-life of about 60 years. The supernova scatters these elements into the surrounding interstellar medium. There, they mix with the ambient hydrogen and helium, enriching the gas from which future generations of stars and planets will form. Our own solar system, born roughly 4.6 billion years ago, condensed from a cloud already enriched by many generations of stellar birth and death. The iron in your blood, the calcium in your bones, the oxygen in every breath you take, all of it was forged in the hearts of stars that died long before our sun was born. But the story of element production does not end with iron. There is an entire upper half of the periodic table still to fill. And to understand how the universe builds elements heavier than iron, we need to understand two different processes. One slow, one fast, each responsible for roughly half of the heaviest elements in existence. Let us start with the slow one. In the outer reaches of a dying red giant star, something quiet and patient is happening. The star has long since exhausted the hydrogen in its core and has been burning helium for tens of thousands of years. It has swollen to hundreds of times the diameter of our sun, its atmosphere a wispy crimson veil extending out past where Mars would orbit. Deep in its interior, in the thin shell where helium fusion is still sputtering along, a delicate nuclear reaction is releasing a steady trickle of neutrons. This is where the S process begins. S stands for slow, and the name is apt. In the S process, an iron nucleus or some other heavy seed nucleus captures a single neutron. This makes it a heavier isotope of the same element. If that new isotope is stable, it simply waits, sometimes for decades, sometimes for centuries, until another neutron happens along and is captured. But if the new isotope is radioactive, it undergoes beta decay before the next neutron arrives. In beta decay, a neutron inside the nucleus converts into a proton, releasing an electron and an antineutrino. This transforms the atom into the next element up on the periodic table. Then that new nucleus waits for another neutron, and the cycle repeats. Step by step, neutron by neutron, the S process climbs the periodic table. It is a slow, methodical journey, hugging the valley of stability in the chart of nuclides, never straying far from the isotopes that nature considers well-balanced. The neutron densities in these stars are modest, roughly 1 million to 1 trillion neutrons per cubic centimeter, which sounds like a lot until you compare it to the conditions in a supernova, where the numbers are incomparably higher. At these moderate densities, the time between successive neutron captures might be tens or hundreds of years. The main site of the S process is a class of stars called asymptotic giant branch stars, or AGB stars. These are stars that started their lives with masses between about 1 and 8 times the mass of the Sun. They have passed through the main sequence, expanded into red giants, and are now in the final stages of their existence. Inside these stars, 2 sources of neutrons power the S process. The primary one is a reaction between carbon-13 and helium-4, which produces oxygen-16 and a free neutron. The carbon-13 itself is created when protons from the star's outer layers are mixed down into the helium-rich intershell region, where they are captured by carbon-12 nuclei. The second neutron source activates during brief, intense episodes called thermal pulses. These occur when the thin helium-burning shell ignites in a flash, briefly generating enormous amounts of energy. During these pulses, a different reaction kicks in. Neon-22 captures a helium-4 nucleus, producing magnesium-25 and a neutron. These thermal pulses happen every few tens of thousands of years, and each one dredges up freshly synthesized material from the deep interior to the star's surface, a process called the third dredge-up. This dredging is critically important. It brings S-process elements, cooked in the star's deep interior, up to the surface, where they can eventually be expelled into space. As the AGB star sheds its outer layers through powerful stellar winds, and eventually ejects them entirely as a planetary nebula. These heavy elements are scattered into the interstellar medium. The S process is responsible for producing roughly half of all isotopes heavier than iron. It builds up the abundances of strontium, yttrium, zirconium, barium, lanthanum, cerium, and lead, among many others. The pattern of S-process abundances has a distinctive sawtooth shape, with peaks at certain magic numbers of neutrons, where nuclei are particularly stable and resistant to further neutron capture. These nuclei act as bottlenecks, accumulating in abundance while the neutron captures slow down around them. The first direct evidence that nucleosynthesis was happening inside stars came in 1952, and it came from the S process. American astronomer Paul Merrill, working at the Mount Wilson Observatory in California, was studying the spectra of certain peculiar red giant stars. In the starlight, decomposed into its component wavelengths by a spectrograph, he found the unmistakable spectral fingerprint of technetium. This was astonishing. Technetium is element 43, and it has no stable isotopes at all. Its longest-lived isotope, technetium-98, has a half-life of about 4.2 million years. That sounds like a long time in human terms, but these red giant stars are billions of years old. Any technetium that might have been present when the star formed would have decayed away long ago. The only possible explanation was that the technetium had been created recently inside the star itself and brought to the surface by convective mixing. It was a smoking gun. Before Merrill's discovery, the idea that stars manufacture elements was a hypothesis, supported by theoretical arguments, but lacking direct observational proof. After his discovery, it was a near certainty. Stars were not merely burning pre-existing fuel. They were nuclear furnaces, building new elements from simpler ingredients and distributing them into the cosmos. But before we dive into the specifics of those two processes, the slow and the rapid, let us pause and consider the people who figured all of this out. Because the story of nucleosynthesis is not just a story about stars. It is also a story about humans, about the brilliance and persistence of a handful of scientists who looked at the cosmos and asked the simplest, most profound question imaginable. Where does all of this stuff come from? The mid-20th century was a time of extraordinary ferment in physics. The atomic bomb had been built and used. Nuclear energy was being harnessed. Particle accelerators were probing the subatomic world with increasing precision, and astrophysics was undergoing a revolution. As new telescopes and new theoretical tools gave scientists unprecedented insight into the lives and deaths of stars. In this environment, the question of element origins was not merely academic. It was one of the deepest mysteries in all of science. The periodic table, that orderly arrangement of elements that hangs in every chemistry classroom on Earth, contains roughly 90 naturally occurring elements. Where had they all come from? Were they all created in the Big Bang? Were they created in stars? Were they relics of some unknown cosmic process? The debate was heated, and it centered on two competing ideas. On one side stood George Gamow and his collaborators. Gamow, a Ukrainian-born physicist with an irrepressible sense of humor and a gift for popularizing science, was convinced that all elements had been synthesized in the extreme conditions of the early universe. He envisioned the Big Bang as a gigantic cosmic furnace in which the entire periodic table was cooked up in a few minutes. His student Ralph Alpher worked out the details, and in 1948, they published their theory. Gamow famously added the name of Hans Bethe to the paper as a joke, so the author list would read Alpher, Bethe, Gamow, a pun on the first three letters of the Greek alphabet. But there was a problem when Alpher and others tried to work out the nuclear reactions in detail. They found that the Big Bang could produce hydrogen and helium in roughly the right proportions. But it hit a roadblock at the mass 5 and mass 8 bottlenecks. Without stable nuclei at those masses, there was no way to bridge the gap from helium to carbon and beyond. The Big Bang could not build the heavy elements. On the other side stood Fred Hoyle. Hoyle was a complicated figure, brilliant, iconoclastic, sometimes abrasive, and occasionally spectacularly wrong. He rejected the Big Bang throughout his life and championed some deeply unorthodox ideas later in his career. But on the question of where the heavy elements come from, he was spectacularly right. Hoyle's 1946 paper, published in the monthly notices of the Royal Astronomical Society, was the first to lay out a coherent case that elements are synthesized inside stars. He argued that under conditions of nuclear statistical equilibrium, at the temperatures found in stellar interiors, the most abundant product would be iron, which matched the observed cosmic abundance pattern perfectly. Iron is about 100 times more abundant than its neighboring elements, a striking peak that Hoyle showed could be naturally explained by stellar nucleosynthesis. 8 years later, in 1954, Hoyle published a far more detailed paper in the Astrophysical Journal supplement, outlining the specific nuclear burning sequences that operate in massive stars: carbon burning, oxygen burning, and silicon burning. He described how the contraction of a star's core after each fuel is exhausted leads to higher temperatures and the ignition of heavier fuels. He described how supernova explosions could eject the products of these reactions into space. It was an extraordinarily prescient paper, and it remains the foundation of our understanding of stellar evolution to this day. The collaboration that led to the B2FH paper began when Hoyle visited Caltech in 1953 and met William Fowler. Fowler was a nuclear experimentalist, not an astrophysicist, but he recognized the importance of Hoyle's ideas immediately. The two men were very different in temperament. Hoyle was a theoretical visionary, sometimes impatient with experimental details. Fowler was methodical, precise, and deeply committed to measuring nuclear reaction rates in the laboratory. Together, they were a powerful team. The Burbages joined the collaboration in 1954 when they traveled to Cambridge to work with Hoyle. Margaret Burbage, born Eleanor Margaret Peachey in Davenport, England, in 1919, was one of the most talented observational astronomers of her generation. She had a particular gift for measuring stellar abundances using spectroscopy, decomposing starlight into its component wavelengths, and reading the chemical fingerprints encoded therein. Her husband Geoffrey was a theorist who helped bridge the gap between observations and theory. The four of them spent nearly 2 years crafting their masterwork. They worked in Cambridge and at Caltech, passing drafts back and forth across the Atlantic. Margaret and Geoffrey Burbage wrote much of the first draft, incorporating their extensive observational data on stellar abundances. Hoyle provided the theoretical framework. Fowler contributed to nuclear physics, drawing on decades of laboratory measurements of nuclear reaction rates. The finished paper, published in October 1957, was 104 pages long. It had no abstract. The editor, Edward Condon, accepted it directly without formal peer review. Such was the reputation of its authors. Hoyle added several quotations from Shakespeare to the opening pages, a characteristically playful touch. The paper identified 8 distinct nucleosynthetic processes and showed how each contributed to the observed pattern of cosmic abundances. It was not merely a theoretical exercise. Every prediction was compared against observational data, primarily the abundances measured by Margaret Burbage and the reaction rates measured by Fowler. The agreement was, in many cases, remarkable. B2FH was not the only paper on nucleosynthesis to appear that year. In a remarkable coincidence, Canadian physicist Alastair Cameron independently published a very similar comprehensive theory of element synthesis in 1957, arriving at many of the same conclusions through different methods. Cameron's work was less well known at the time, partly because it appeared as an Atomic Energy of Canada report rather than in a major journal. But it was equally groundbreaking. history has been kinder to B2FH, but Cameron deserves recognition as one of the true pioneers of nuclear astrophysics. The legacy of B2FH extended far beyond its immediate scientific impact. It inspired a generation of nuclear astrophysicists to pursue the question of element origins with renewed vigor. Laboratories around the world began measuring the nuclear reaction rates needed to refine the predictions. Astronomers embarked on systematic surveys of stellar abundances, testing and extending the theory. Theorists developed increasingly sophisticated models of stellar evolution, tracking the buildup of elements through each stage of a star's life, and the results kept confirming the essential picture laid out by Hoyle, the Burbages, and Fowler. With each passing decade, the theory of stellar nucleosynthesis became more detailed, more precise, and more firmly established. There were surprises along the way. Some predicted reaction rates turned out to be wrong when measured in the laboratory, requiring revisions to the abundance calculations. New nucleosynthetic processes were discovered that B2FH had not anticipated, but the core insight that nearly all elements heavier than lithium are forged inside stars has only grown stronger with time. And it was one particular process described in B2FH that would remain deeply mysterious for decades: the R process. The paper identified it, described its theoretical requirements, and calculated the isotopes it should produce. But for over half a century, no one could say for certain where it occurred. The S process, remember, needs seed nuclei to work with. It cannot create heavy elements from scratch. It needs a starting point, typically iron or nearby elements that were produced by a previous generation of stars. Iron nuclei act as the foundation upon which the S process builds, one neutron at a time, constructing heavier and heavier elements along the valley of stability. This means the S process is what physicists call a secondary process. It can only operate in stars that already contain some iron from previous cycles of stellar birth and death. This has important implications for the chemical history of the universe. The very first generation of stars, formed from the pure hydrogen and helium of the Big Bang, would have had no iron seeds. The S process could not have operated in those stars, at least not in the way we observe it today. The heavy elements produced by the first stars came primarily from the R process and from explosive nucleosynthesis in their supernova deaths. It was only after these first stars had lived, died, and enriched the interstellar medium with their products that subsequent generations of stars could begin S-process nucleosynthesis. The consequences of this timeline are written in the chemistry of the oldest surviving stars. Astronomers have found extremely metal-poor stars in the halo of our galaxy, ancient relics from the earliest epochs of star formation that display unmistakable R-process abundance patterns, but very little evidence of S-process contributions. These stars are chemical fossils, preserving in their atmospheres a record of the nucleosynthesis that occurred in the first generations of massive stars. By studying their compositions, astronomers can reconstruct the chemical evolution of the galaxy, tracing how different nucleosynthetic processes turned on and contributed their products over billions of years. One such star, designated CS 22892-52, discovered in the 1990s, showed a remarkably clean R-process abundance pattern in its atmosphere. The ratios of heavy elements matched the theoretical R-process predictions almost perfectly, with virtually no S-process contamination. This star must have formed from gas enriched by one or a few R-process events, probably supernovae or neutron star mergers in the very early galaxy. It was living proof that the R-process operated early in cosmic history, before the S-process had a chance to contribute significantly. But let us return to the S-process itself, and to the extraordinary journey that each heavy atom takes inside an AGB star. Imagine you are an iron 56 nucleus, sitting comfortably in the intershell region of an AGB star. You have been there for thousands of years, ever since the star's convective motions carried you down from the surface. The temperature around you is tens of millions of degrees. The density is high. And every so often, perhaps once every few decades, a free neutron wanders close enough for you to capture it. When you capture that neutron, you become iron 57. This is a stable isotope, so you simply wait. Another few decades pass, and you capture another neutron, becoming iron 58. Also stable. You wait again. Eventually, you capture enough neutrons to become iron 60, which is radioactive. It beta decays, turning one of its excess neutrons into a proton and becoming cobalt 60. Cobalt 60 is also radioactive and decays into nickel 60, which is stable. Now you are nickel, a different element than you started as. The process continues. You capture more neutrons, occasionally beta decaying to climb up the periodic table. Nickel becomes copper. Copper becomes zinc. Zinc becomes gallium, germanium, arsenic, selenium, and onward. At certain points, you encounter the magic neutron numbers 50, 82, and 126, where nuclear shells are complete, and the nucleus becomes especially stable and especially reluctant to capture another neutron. The S-process slows down at these bottleneck nuclei, and they accumulate in abundance, creating the characteristic peaks in the S-process abundance distribution at strontium, barium, and lead. Lead, element 82, is essentially the end of the line for the S-process. Beyond lead, the isotopes become increasingly unstable, and the S-process path runs into a dead end at bismuth 209, the heaviest stable, or very nearly stable, with a half-life vastly longer than the age of the universe. Nucleus. Beyond bismuth, any isotope formed by neutrons quickly alpha decays, spitting out a helium nucleus and dropping back down to lead or bismuth. The S-process cycles between lead, bismuth, and polonium, unable to advance further. This is why lead is the dominant final product of the S-process. The oldest, most metal-poor AGB stars in the galaxy, whose S-process had very little iron to work with but plenty of neutrons per seed nucleus, produced enormous amounts of lead relative to other heavy elements. These lead-rich stars are a beautiful confirmation of our theoretical understanding of the S-process. Now, while the S-process is doing its patient work in AGB stars, let us turn our attention to another way that stars produce and distribute elements, one that involves a very different kind of stellar death. We have already discussed the core collapse supernovae that end the lives of massive stars. But there is another class of supernovae that plays a crucial role in the cosmic element budget. Type 1a supernovae. These explosions do not come from massive stars. Instead, they come from white dwarfs, the burned-out remnants of lower-mass stars. A white dwarf is the exposed core of a star that has shed its outer layers, leaving behind a ball of carbon and oxygen, or sometimes oxygen and neon, roughly the size of Earth, but with a mass comparable to the Sun's. White dwarfs are supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect that arises because electrons resist being packed too closely together. Left to its own devices, a white dwarf would simply cool and fade over trillions of years, eventually becoming a cold, dark cinder called a black dwarf. But many white dwarfs are not alone. They exist in binary systems, orbiting close to a companion star. And if that companion is close enough, the white dwarf's gravity can strip material from the companion's outer layers, pulling a stream of gas down onto the white dwarf's surface. As this accreted material piles up, the mass of the white dwarf grows. And when it approaches the Chandrasekhar limit, roughly 1.4 solar masses, something remarkable happens. The temperature and density in the white dwarf's interior rise to the point where carbon can ignite. But this is not the gentle, controlled burning that occurs in the core of a main sequence star. This is a runaway thermonuclear detonation. In a matter of seconds, a nuclear flame rips through the entire white dwarf, fusing its carbon and oxygen into heavier elements. The inner regions, where densities are highest, undergo complete nuclear burning, producing iron group elements, primarily nickel-56. The outer layers undergo incomplete burning, producing intermediate mass elements like silicon, sulfur, calcium, and magnesium. The energy released is so enormous, roughly 1 × 10⁴ joules, that it completely unbinds the white dwarf. The entire star is blown apart, leaving no remnant behind. Nothing. Just an expanding cloud of hot debris laced with radioactive nickel-56. As the debris expands and cools, the nickel-56 decays to cobalt-56 with a half-life of about 6 days, and then the cobalt-56 decays to stable iron-56 with a half-life of about 77 days. The energy released by this radioactive decay chain powers the visible light of the supernova, causing it to brighten to a peak luminosity of roughly 5 billion suns, before gradually fading over the following months as the cobalt-56 is consumed. Type 1a supernovae are incredibly important to cosmology because they are remarkably uniform in their peak brightness. Since the explosion always occurs near the Chandrasekhar limit, the amount of nickel-56 produced, and therefore the peak luminosity, is roughly the same from one event to the next. This makes them excellent standard candles for measuring cosmic distances. It was the use of Type 1a supernovae as distance indicators that led to the discovery, in 1998, that the expansion of the universe is accelerating. A finding that earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. But for our story, the importance of Type 1a supernovae lies in their role as element factories. Each event produces roughly 0.6 of a solar mass of iron, making them the single most important source of iron in the universe. They are also major producers of manganese, chromium, nickel, and cobalt. The iron in your blood, in every steel bridge, in every kitchen knife on Earth, was overwhelmingly produced by Type 1a supernovae over the history of the Milky Way. There is an alternative scenario for Type 1a supernovae that has gained significant support in recent years: the double degenerate model. In this scenario, instead of a white dwarf accreting material from a companion star, 2 white dwarfs in a close binary system gradually spiral together due to the loss of energy through gravitational wave emission. When they merge, the combined mass exceeds the critical threshold for detonation, and the thermonuclear explosion follows. The nucleosynthetic yields are broadly similar in both scenarios, producing large amounts of iron group elements, though the details differ in ways that astronomers are still working to disentangle. There is even a class of subchandrasekhar mass explosions, where a white dwarf well below 1.4 solar masses detonates due to a surface layer of accreted helium, igniting and driving a shock wave into the carbon-oxygen core. These produce somewhat different abundance patterns, with less nickel-56 and correspondingly dimmer explosions. The diversity of Type 1a supernovae is a rich and active area of research, but now it is time to turn our attention to the other great neutron capture process, the one that B2FH described but could not fully explain. The rapid process, the R process, if the S process is a patient craftsman, carefully placing one brick at a time, the R process is an explosion in a brick factory. It is chaotic, violent, and astonishingly fast. In the R process, a seed nucleus is bombarded with such an intense flux of free neutrons that it captures them far faster than any unstable isotope can decay. The nucleus gorges itself on neutrons, ballooning into increasingly neutron-rich and unstable configurations that do not exist under normal circumstances anywhere in the universe. These grotesquely swollen nuclei sit far from the valley of stability in the nuclear chart, in regions that nuclear physicists have barely begun to explore experimentally. Only when the neutron bombardment finally ceases, when the supply of free neutrons is exhausted, do these bloated nuclei begin to decay. Through cascading chains of beta decays, they shed their excess neutrons by converting them into protons, climbing back toward stability and producing a characteristic pattern of R process abundances. The R process is responsible for about half of all isotopes heavier than iron. It produces all of the naturally occurring uranium and thorium, most of the platinum and gold, and many other heavy elements. Its fingerprint is a distinctive pattern of abundance peaks at atomic mass numbers around 80, 130, and 195, corresponding to neutron magic numbers, where particularly stable nuclear configurations create bottlenecks in the capture process. To appreciate the scale of the R process, consider this. In a typical R process event, a single nucleus might capture 50 or 60 neutrons in the space of a few seconds. The neutron densities required are staggering, roughly 10 to the 20th neutrons per cubic centimeter or higher. At these densities, the time between successive neutron captures drops to milliseconds or less. The nucleus has no time to beta decay between captures. It simply absorbs neutron after neutron, growing fatter and more unstable with each addition, like a balloon being inflated past its breaking point. The conditions needed to sustain this kind of neutron bombardment are extraordinarily demanding. You need a dense environment rich in free neutrons, with temperatures in the billions of degrees. And you need the whole thing to happen fast enough that the neutrons do not all decay before they can be captured. For decades, the leading candidate was the neutrino-driven wind from a newly born neutron star in a core collapse supernova. The idea was compelling. During the seconds and minutes after the neutron star forms, a hot wind of material streams off its surface, driven by the intense neutrino flux. As this material expands and cools, conditions might be right for rapid neutron capture. But detailed computer simulations kept running into problems. The neutron-to-proton ratio in the supernova wind turned out to be stubbornly close to equal, not neutron-rich enough for a robust R process. The conditions needed to produce the heaviest R process elements, like gold, platinum, and uranium, were extremely difficult to achieve. Some lighter R process elements might be produced in supernova winds, but the heaviest elements seemed to require something even more extreme. The search for the R process site became one of the great detective stories of modern astrophysics. Theorists proposed alternative scenarios. Some suggested that rare, energetic supernovae associated with rapidly rotating, highly magnetized neutron stars called magnetars might provide the right conditions. Others pointed to collapsers, the energetic jet-driven explosions produced when the core of a very massive star collapses directly to a black hole. Still, others proposed that the accretion disk of material that forms around a newly born black hole in such an event could be neutron-rich enough to drive a full R process. But there was another candidate that had been discussed since the 1970s, one that seemed almost too rare and too exotic to be the dominant source: the merger of two neutron stars. The idea was first proposed by James Latimer and David Schramm in 1974. They realized that when two neutron stars merge, the collision would eject a small but significant amount of extremely neutron-rich material. Since neutron stars are, by definition, made almost entirely of neutrons, the ejected material would have the exact neutron-rich composition needed for an R process. The problem was that neutron star mergers were predicted to be exceedingly rare, perhaps happening only once every 10,000 to 100,000 years in a galaxy the size of the Milky Way. Could such rare events really be the dominant source of half the heavy elements in the universe? For decades, the question remained unanswered. Then came August 17, 2017, and everything changed. The story of G170,817 deserves to be told in full, because it represents one of the most remarkable scientific achievements of the 21st century. The gravitational wave signal was first detected by the LIGO detector in Hanford, Washington, followed milliseconds later by the LIGO detector in Livingston, Louisiana, and the Virgo detector in Cassina, Italy. The signal lasted about 100 seconds, rising in frequency from about 24 Hz to several hundred Hz as the two neutron stars spiraled ever faster and closer. By analyzing the rate at which the frequency increased, physicists could determine the masses of the two objects, roughly 1.4 and 1.2 solar masses, respectively. Both were consistent with neutron stars rather than black holes. The detection of the short gamma-ray burst just 1.7 seconds after the gravitational wave signal ended was electrifying. For decades, astronomers had theorized that short gamma-ray bursts were produced by neutron star mergers. Now, for the first time, they had simultaneous gravitational waves and electromagnetic confirmation. The hypothesis was confirmed in a single observation. But the real treasure was the kilonova. And to understand what a kilonova is, you first need to understand what happens when two neutron stars actually collide. Each neutron star is roughly 12 kilometers across, about the size of a mid-sized city. Yet it contains 1 to 2 solar masses of material compressed to densities exceeding that of an atomic nucleus. To put this in perspective, a single teaspoon of neutron star material would weigh roughly 6 billion tons on the surface of the Earth. If you could somehow transport a sugar cube-sized chunk of a neutron star to your kitchen table, it would weigh as much as a mountain. These objects are so dense that their surfaces curve spacetime dramatically, with gravitational fields roughly 200 billion times stronger than what you feel standing on the ground right now. As the two stars spiral closer in those final moments, they do not simply crash together like billiard balls. The last phase is a complex gravitational dance. In the final orbits, tidal forces begin to distort the neutron stars, stretching them into elongated shapes. The stars are orbiting each other hundreds of times per second by this point, their orbital frequency increasing relentlessly as gravitational wave emission drains energy from the system. The gravitational waves are so powerful that they carry away energy equivalent to several percent of the total mass energy of the system. When the stars finally make contact, temperatures at the collision interface soar past 50 billion degrees. Tidal forces tear material from their surfaces, flinging neutron-rich matter outward at a significant fraction of the speed of light. A massive shockwave propagates outward through the collision debris. Additional material is ejected by the instabilities and turbulence of the merger itself, and by winds from the spinning disk of debris that briefly forms around the merger remnant. In some cases, a hypermassive neutron star might survive for a few tens of milliseconds before collapsing into a black hole, driving additional outflows through its intense magnetic fields and powerful neutrino emission. This ejected material is extraordinarily neutron-rich, far more so than anything found in a supernova environment. And it is in this neutron-rich debris that the R process runs wild. Within seconds of the ejection, free neutrons are captured by seed nuclei at rates of up to 100 captures per second. The nuclei are driven far into the uncharted neutron-rich wilderness of the nuclear chart, building up to the heaviest elements in nature. As these unstable nuclei decay, they release energy in the form of gamma rays and energetic particles. This radioactive heating powers the kilonova, making the expanding debris glow across the electromagnetic spectrum. The optical counterpart of G 170,817, discovered 11 hours after the merger in the galaxy NGC 4993, initially appeared blue-white, consistent with emission powered by the decay of lighter R process elements. Over the following days, it reddened dramatically, shifting into the near-infrared. This was the signature of lanthanide elements, a group of heavy R process products that includes elements like neodymium, europium, and gadolinium. Lanthanides have complex electron configurations that produce an extraordinary number of spectral lines, creating an opacity so high that they effectively trap blue light and re-emit it at longer, redder wavelengths. The two-component behavior of the kilonova, blue early and red later, matched theoretical predictions almost perfectly. It indicated that the merger had produced two distinct components of ejecta, a relatively neutron-poor component, perhaps from shock-heated material at the contact interface of the two stars, that produced lighter R process elements, and a more neutron-rich component, perhaps from tidal tails or disk winds, that produced the full range of heavy R process elements up to and including gold, platinum, and uranium. In 2019, a team of astronomers, including Darach Watson and Camilla Hansen, published a detailed analysis of the spectra taken by the Very Large Telescope in Chile during the kilonova. they identified absorption features at around 350 nanometers and 850 nanometers that could only be produced by strontium, element 38. It was the first time a specific R-process element had been spectroscopically identified in a kilonova. Strontium, a silvery metal that you might recognize from the red color it produces in fireworks, was being produced in vast quantities by the collision of two neutron stars 140 million light-years away. The total mass of R-process elements produced by G170,817 was estimated at between 1 and 5/100ths of a solar mass, a seemingly small number, until you realize that this includes roughly 10 Earth masses of gold and 10 Earth masses of platinum. In a single event lasting seconds, the merger produced more precious metals than exist on our entire planet many times over. This raises a profound question. Is all of the gold on Earth, and indeed all of the R-process elements in the solar system, the product of a single ancient neutron star merger? Or were multiple mergers required? The answer depends on the rate of neutron star mergers in the galaxy and the amount of R-process material each one produces. Current estimates suggest that neutron star mergers occur in the Milky Way roughly once every 10,000 to 100,000 years over the 10 billion year history of the galaxy. That amounts to somewhere between 100,000 and a million mergers. If each one produces roughly as much R-process material as G170,817 did, the cumulative total is broadly consistent with the amount of R-process elements observed in the solar system and across the galaxy. However, there are complications. Some researchers have pointed out that neutron star mergers may not be able to explain the R-process enrichment observed in the very oldest stars and in ultra-faint dwarf galaxies, where the enrichment appears to have happened very early, perhaps before enough neutron star binaries had time to merge. This has led to renewed interest in rare types of core-collapse supernovae, particularly collapsers, the energetic jets produced when a massive star collapses to form a black hole. As additional R-process sites, the relative contributions of mergers and supernovae to the total R-process budget remain a subject of active debate. But whether neutron star mergers are the sole source or merely the dominant source of heavy R-process elements, the observation of G170,817 has fundamentally changed our understanding of where the heaviest elements come from. Before 2017, the R-process was a theoretical construct with circumstantial evidence pointing to various possible sites. After G170,817, it was an observed reality. Let us now gather all these threads together and contemplate the full picture of cosmic nucleosynthesis, the complete account of how the universe populated the periodic table. It begins in the first 20 minutes. The Big Bang nucleosynthesis produces hydrogen and helium, with traces of deuterium, helium-3, and lithium-7. The universe is chemically simple, consisting of just 3 elements. Hundreds of millions of years later, the first stars form. In their cores, hydrogen fuses to helium through the proton-proton chain and the CNO cycle. These stars also produce small amounts of nitrogen and traces of other light elements during their main sequence lifetimes. But the first truly significant additions to the periodic table come when these massive stars die. In the final stages of massive star evolution, the successive burning of helium, carbon, neon, oxygen, and silicon, constructs elements up to iron. Each burning stage proceeds more rapidly than the last, the star burning through fuel at an accelerating pace until the iron core forms and the star's energy supply is exhausted. The core collapse supernova that follows not only ejects these elements into space, but also triggers explosive nucleosynthesis that produces additional elements, particularly in the silicon and oxygen shells that are heated by the passing shockwave. The R process may operate in the neutrino-driven winds from the newly formed neutron star, or in the material ejected during the collapse, producing some heavy elements beyond iron. Meanwhile, intermediate mass stars evolve more slowly. Over billions of years, they ascend the asymptotic giant branch, where the S process operates in their helium-burning shells, building heavy elements from iron seeds through patient, slow neutron capture. These stars shed their enriched outer layers through stellar winds and planetary nebulae, seeding the interstellar medium with S-process products. White dwarfs in binary systems occasionally explode as Type 1a supernovae, producing enormous quantities of iron peak elements and scattering them into space. These events occur on longer timescales than core collapse supernovae, gradually enriching the galaxy with iron, nickel, and manganese. Throughout all of this, cosmic ray spallation operates as a low-level but persistent background process, producing lithium, beryllium, and boron through the shattering of heavier nuclei by energetic particles, and periodically, neutron star mergers occur. Two neutron stars, the remnants of ancient supernovae, spiral together and collide, releasing a flood of R-process material that enriches the galaxy with the heaviest elements: gold, platinum, uranium, thorium, and many more. Each generation of stars forms from gas that has been enriched by all of these processes combined. The first stars had only hydrogen and helium. The second generation had small amounts of heavier elements from the first generation's supernovae. And with each successive generation, the metallicity of the galaxy increased, the gas becoming richer and richer in heavy elements. Our Sun, a relatively young star at roughly 4.6 billion years old, formed from gas that had been enriched by billions of years of chemical evolution. The enrichment is not uniform across the galaxy. Different regions have different chemical histories depending on their star formation rates, their proximity to recent supernovae or merger events, and the dynamics of gas flows and mixing. Some regions are more metal-rich, others more metal-poor. Some show enhancement in R-process elements, suggesting a nearby merger event in their past. Others show predominantly S-process signatures, suggesting enrichment from a population of AGB stars. The chemical composition of stars is a window into the history of the gas from which they formed, and through it, the history of nucleosynthesis in that particular corner of the galaxy. Astronomers call this cosmic chemical evolution, and mapping it out, galaxy by galaxy, star by star, element by element, is one of the great ongoing projects of modern astrophysics. Consider what it means for our own solar system. The particular mix of elements that makes up the Earth, the Sun, and everything in our solar system is the cumulative product of roughly 9 billion years of chemical evolution in the Milky Way. Billions of stars lived and died before our Sun was born, each one contributing its particular products to the interstellar medium. Our solar system's composition reflects the integrated output of all those stars, weighted by their masses, their lifetimes, and the efficiency with which they returned their products to the gas. The silicon in the Earth's crust came from oxygen and carbon burning in massive stars. The iron in the Earth's core came from both core collapse and thermonuclear supernovae. The uranium that powers the Earth's internal heat, driving plate tectonics, and the magnetic field that shields us from cosmic radiation, was produced by the R process in neutron star mergers, or supernovae. The carbon in every living molecule was forged by the triple alpha process in red giant stars. The oxygen we breathe was produced by helium burning in massive stars and ejected in their supernova deaths. We can even trace specific isotopic ratios in meteorites to particular nucleosynthetic sources. Certain microscopic grains found in primitive meteorites, called prosolar grains, are actual pieces of ancient stars. Tiny particles of silicon carbide or diamond or oxide that condensed in the outflowing winds of AGB stars, or in the expanding debris of supernovae billions of years ago. These grains survived the formation of the solar system and were incorporated into the meteorites we find on Earth today. By analyzing their isotopic compositions, scientists can identify the specific type of star that produced them and the specific nuclear processes at work in that star. It is, in a very real sense, stellar archaeology. Each grain is a message in a bottle from a long-dead star, carrying information about the nuclear reactions that occurred in its interior. One of the more poignant examples is the prosolar silicon carbide grains that carry the isotopic fingerprints of the S process. These grains condensed in the atmospheres of AGB stars, trapping the heavy element signatures that had been dredged up from the star's interior. When scientists measure the isotopic ratios of elements like barium, strontium, and krypton in these grains, they find patterns that match theoretical S-process predictions with remarkable precision. Each grain is a frozen snapshot of the nuclear reactions occurring in a star that died before our solar system existed. The universe, it turns out, keeps meticulous records, and we are slowly learning to read them. Now, you may have noticed that there are a few elements we have not yet accounted for. The Big Bang produced hydrogen, helium, and traces of lithium. Stars produce everything from carbon to iron through successive stages of nuclear fusion. Supernovae produce iron peak elements through explosive nucleosynthesis. And both supernovae and neutron star mergers produce the heavy elements beyond iron through the R process and S process. White dwarf explosions, the type 1a supernovae, also contribute significantly to the iron peak elements, particularly iron, nickel, cobalt, chromium, and manganese. But what about lithium, beryllium, and boron? These three light elements occupy a peculiar place on the periodic table. They sit between helium and carbon, right in the gap created by the mass 5 and mass 8 bottlenecks. The Big Bang produces a small amount of lithium-7, but not nearly enough to explain all the lithium we observe, and essentially no beryllium or boron. Stars do not produce these elements either. In fact, stars destroy them. Lithium, beryllium, and boron nuclei are relatively fragile, with low binding energies, and they are quickly broken apart by the high temperatures inside stellar interiors. So where do they come from? The answer is one of the more unusual stories in nucleosynthesis: cosmic ray spallation. High-energy particles, primarily protons and heavier atomic nuclei, accelerated to nearly the speed of light by supernova shockwaves and other energetic phenomena, streak through interstellar space. when one of these cosmic ray particles slams into a heavier nucleus floating in the interstellar medium, like a carbon or oxygen atom. The collision is so violent that it shatters the target nucleus into smaller fragments. These fragments include lithium, beryllium, and boron nuclei. It is a destructive process, not a constructive one. Elements are being broken apart rather than built up, but the fragments that result are precisely the light elements that no other process can produce in significant quantities. Cosmic ray spallation is the primary source of beryllium-9, the only stable isotope of beryllium, boron-10, boron-11, and lithium-6. Lithium-7 comes from a combination of Big Bang production, cosmic ray spallation, and possibly nova eruptions, where thermonuclear explosions on the surfaces of white dwarfs may create significant quantities. The discovery that cosmic ray spallation could produce these elements came somewhat by accident in the 1970s. Researchers had been investigating whether cosmic rays could explain an apparent excess of deuterium in the universe. They found that spallation was not very efficient at producing deuterium, but in the process, they noticed it was extremely good at producing lithium, beryllium, and boron. The abundances of these elements in cosmic rays are dramatically higher than in the atmospheres of stars, precisely because cosmic ray collisions are continuously creating them in interstellar space, and so the picture is complete, or nearly so. The periodic table is populated by a remarkable collection of processes, each operating under different conditions, at different times, and in different locations across the cosmos. Hydrogen and most of the helium date back to the first 20 minutes of the universe. Carbon, nitrogen, oxygen, and the other intermediate elements are forged in the cores of stars over millions and billions of years. Iron and its neighbors are the end products of fusion in the most massive stars, and are also produced in abundance by thermonuclear supernovae. The elements heavier than iron are built by the S process in aging giant stars and the R process in neutron star mergers. And to some extent, supernovae and the fragile light elements, lithium, beryllium, and boron, are produced by the cosmic ray bombardment of interstellar gas. There is also a less commonly discussed process called the P process, or sometimes the gamma process, which is responsible for producing a small number of proton-rich isotopes of heavy elements that cannot be made by either the S process or the R process. These isotopes are typically produced when intense gamma radiation in supernova explosions knocks neutrons out of existing heavy nuclei through photodisintegration, leaving behind proton-rich remnants. The P-process isotopes are rare, often 100 or 1,000 times less abundant than their S-process and R-process cousins. But they complete the picture of how the full range of nuclear species came to be. There are also more recently identified processes, like the intermediate neutron capture process, or I process, which operates at neutron densities between those of the S process and the R process. The I process has been proposed to explain unusual abundance patterns observed in certain metal-poor stars that cannot be accounted for by either the S process or R process alone. It may occur in special environments, such as during the ingestion of hydrogen into a helium-burning shell, creating a brief but intense burst of neutrons. The I process is still being studied, and its relative importance in the overall scheme of nucleosynthesis is an active area of investigation. But even as the picture has become increasingly complete, there are significant puzzles that remain stubbornly unsolved. And perhaps the most famous of these is the lithium problem. As we discussed, Big Bang nucleosynthesis produced a small but calculable amount of lithium-7. The predictions of primordial nucleosynthesis are exquisitely sensitive to the conditions in the early universe, particularly the ratio of baryons to photons, which has been precisely measured by observations of the cosmic microwave background radiation. Using this measured value, theorists can predict exactly how much lithium-7 the Big Bang should have produced. The prediction is clear and precise. But when astronomers measure the amount of lithium-7 in the atmospheres of the oldest, most metal-poor stars in the galaxy, stars that should have preserved the primordial lithium abundance relatively unchanged, they find roughly 3 times less lithium than the theory predicts. This discrepancy, first identified in the 1980s by French astronomers Monique and François Spite, has persisted for decades despite enormous efforts to resolve it. It is known as the cosmological lithium problem, and it remains one of the most vexing open questions in astrophysics. Numerous explanations have been proposed. Perhaps the old stars have destroyed some of their lithium through mixing processes that bring surface material down to hotter layers where lithium is broken apart. Perhaps there are subtle errors in the nuclear reaction, rates used to calculate primordial lithium production. Perhaps new physics beyond the standard model of particle physics, such as the decay of exotic particles in the early universe, altered the primordial abundances in ways we have not yet accounted for. None of these explanations has proven fully satisfactory, and the lithium problem continues to motivate both observational campaigns and theoretical research. The unsolved mysteries do not end there. While G170,817 provided spectacular confirmation that neutron star mergers produce R-process elements, the details of how the R-process operates within those mergers are still being worked out. The nuclear physics of the R-process path involves thousands of extremely neutron-rich isotopes, most of which have never been produced or studied in any laboratory on Earth. Their masses, decay rates, and neutron capture cross-sections are largely unknown, and yet these properties determine the exact pattern of elements that the R-process produces. Without accurate nuclear data, our models of R-process nucleosynthesis rely on theoretical extrapolations that may be significantly wrong. This is where a new generation of experimental facilities enters the story. The Facility for Rare Isotope Beams, known as FRIB, began operations at Michigan State University in 2022. FRIB is designed to produce and study the exotic, short-lived nuclei that lie along the R-process path by accelerating beams of heavy ions to enormous speeds and smashing them into targets. FRIB can create nuclei that have never existed on Earth before. Nuclei with wildly unbalanced ratios of protons to neutrons that survive for only fractions of a second. By measuring the properties of these nuclei, scientists can replace the theoretical guesses in R-process models with actual experimental data. Early results from FRIB have already begun to refine our understanding of R-process nucleosynthesis. Measurements of certain neutron-rich isotopes near mass number 80 have revealed surprises in their nuclear structure that alter the predicted R-process abundance pattern in that region. As FRIB pushes toward producing even more exotic nuclei in the coming years, each new measurement will bring the theoretical predictions closer to reality. Meanwhile, the James Webb Space Telescope, launched in December 2021, is opening new windows on nucleosynthesis in the very early universe. By observing galaxies at extreme distances, Webb is seeing the universe as it was within the first few 100 million years after the Big Bang, when the very first stars were living and dying. The chemical abundances imprinted in the spectra of these early galaxies carry information about what those first stars produced and how quickly the universe enriched itself with heavy elements. Some early Webb observations have already yielded surprises. Certain galaxies observed at very high redshifts appear to be chemically enriched beyond what standard models of stellar evolution predict for such young cosmic ages. This suggests that the processes of element production and distribution in the early universe may have been more efficient than previously assumed, possibly due to the unusual properties of population 3 stars, or to nucleosynthesis in exotic environments like parent stability supernovae. Titanic explosions produced by stars with masses exceeding 140 times that of the Sun. Gravitational wave observatories, too, continue to advance. The fourth observing run of LIGO and Virgo, which began in 2023, has detected additional neutron star merger candidates, each one a potential new laboratory for studying our process, nucleosynthesis. Future detectors like the proposed Einstein telescope in Europe and Cosmic Explorer in the United States will be sensitive enough to detect neutron star mergers throughout the observable universe, providing a statistical census of how much our process material these events produce over cosmic time. And on the ground, massive stellar surveys like Galah, Apogee, and the forthcoming surveys planned for the Vera Rubin Observatory are cataloging the chemical compositions of millions of stars across the Milky Way. Each star is a data point in the galaxy's chemical history, and by analyzing the patterns of abundances across different stellar populations, astronomers are reconstructing the history of nucleosynthesis in our galaxy with unprecedented detail. They call this field galactic archaeology, and its goal is nothing less than a complete chemical history of the Milky Way, from the first stars to the present day. The results are painting a picture of remarkable complexity, different parts of the galaxy enriched at different rates. The thick disk of the Milky Way, composed of older stars, shows different abundance ratios than the thin disk, composed of younger stars. The galactic bulge has its own distinctive chemical signature. Satellite dwarf galaxies orbiting the Milky Way, many of which were absorbed and torn apart by our galaxy's gravity over billions of years, left behind streams of stars with chemical compositions that reflect their own independent histories of nucleosynthesis. By tracing these streams and analyzing their chemistry, astronomers can piece together the merger history of the Milky Way itself, reading the story of our galaxy's assembly written in the elemental abundances of its stars. There are also more recently identified processes, like the intermediate neutron capture process, or I process, which operates at neutron densities between those of the S process and the R process. The I process has been proposed to explain unusual abundance patterns observed in certain metal-poor stars that cannot be accounted for by either the S process or R process alone. It may occur in special environments, such as during the ingestion of hydrogen into a helium-burning shell, creating a brief but intense burst of neutrons. And let us not forget the Type 1a supernovae. These are not core collapse supernovae of massive stars. Instead, they are thermonuclear explosions of white dwarf stars in binary systems. When a white dwarf accumulates enough mass from a companion star, or when two white dwarfs merge, the carbon and oxygen in the white dwarf can be ignited in a runaway nuclear reaction. The resulting explosion is extraordinarily bright and completely destroys the white dwarf, leaving no remnant behind. In a matter of seconds, the thermonuclear flame tears through the star, fusing its carbon and oxygen into heavier elements, primarily nickel-56, which later decays to cobalt-56, and then to iron-56. A single Type 1a supernova produces roughly 6/10 of a solar mass of iron, about 10 times more iron per event than a typical core collapse supernova. Type 1a supernovae are the primary source of iron in the universe. They are also major producers of nickel, cobalt, chromium, and manganese because they occur on longer timescales than core collapse supernovae, taking hundreds of millions to billions of years for the white dwarf to accumulate enough mass. They enriched the galaxy with iron peak elements later than the core collapse supernovae, enriched it with oxygen, silicon, and the alpha elements. This time delay leaves a characteristic chemical fingerprint in the oldest stars of the Milky Way, which tend to be enriched in alpha elements like oxygen and magnesium relative to iron. A pattern that gradually changes as Type 1a supernovae begin to contribute their iron to the interstellar medium. But beyond nuclear physics and astrophysics, beyond the equations and the observations and the laboratory measurements, there is something deeper happening here. Something that connects the story of nucleosynthesis to the story of our own existence in a profound and humbling way. Every atom in your body has a history, and not just a vague, poetic history, a specific, traceable, scientifically reconstructible history. The hydrogen atoms in your water molecules have been around since the first few minutes of the universe, 13.8 billion years ago. They are primordial, the oldest material in your body, older than any star, older than any galaxy. When you drink a glass of water, you are consuming atoms that were forged in the firestorm of creation itself. The carbon atoms in your DNA were forged by the triple alpha process in the core of a red giant star that lived and died billions of years before our sun formed. That star swelled to enormous size, dredged up its newly synthesized carbon, and expelled it into space in a glowing planetary nebula. The carbon drifted through interstellar space for millions of years before being incorporated into the collapsing cloud that became our solar system. From there, it found its way into the molecules that make up the genetic code of every living thing on this planet. The oxygen you are breathing right now was fused from carbon and helium in a massive star that exploded as a supernova, scattering its contents across a region of space hundreds of light years wide. That oxygen mixed with the ambient interstellar gas was swept up by the gravitational collapse of a new stellar nursery and eventually became part of the atmosphere of a small rocky planet orbiting a young yellow star. You inhale it with every breath. You could not survive without it. And yet it was produced in a cataclysm so violent that it briefly outshone an entire galaxy. The calcium in your bones was produced in the oxygen-burning shell of a dying star, in a thin layer sandwiched between shells of neon and silicon, at temperatures of roughly 2 billion degrees. The iron in your hemoglobin, the protein that carries oxygen through your bloodstream, is the ash of silicon burning, the last constructive act of nuclear fusion in a massive star before its core collapses. And it dies in a blaze of neutrinos and light, and the trace elements that you carry, the zinc in your enzymes, the iodine in your thyroid, the selenium in your antioxidant proteins, the copper in your blood. These were built atom by atom through neutron capture in AGB stars, or blasted into existence in the extreme conditions of a supernova or a neutron-star merger. The gold in your jewelry, if you are wearing any, was forged when two neutron stars, each denser than an atomic nucleus, spiraled together and collided at a third of the speed of light, releasing more energy in seconds than the sun will produce in 10 billion years. Every single element has a story. Fluorine, which keeps your teeth from decaying, is produced in a complex chain of reactions during supernova explosions and in the helium-burning shells of AGB stars. And its exact production pathway remains a matter of active scientific debate. Phosphorus, without which the DNA molecule could not exist, and every living cell on Earth would cease to function, is produced primarily during neon and oxygen burning in massive stars. Tin, which humans have used for thousands of years to make bronze and to preserve food, is an S-process element, built up from lighter nuclei in the interiors of red giant stars over tens of thousands of years. Even the radioactive elements play a role. The uranium and thorium in the Earth's mantle, produced exclusively by the R process, are decaying right now, and the heat they generate drives the convective currents in the Earth's interior that power plate tectonics. Without those R process elements, the Earth would have cooled more quickly, its interior solidifying, its magnetic field weakening or disappearing entirely. Without the magnetic field, the solar wind would have stripped away our atmosphere, as it did on Mars. The habitability of our planet, in a very real sense, depends on elements that were forged in the collision of neutron stars billions of years before the Earth existed. Think about that for a moment. The story of nucleosynthesis is not some abstract exercise in physics. It is the story of how everything around you came to be. The silicon in the glass of your window was fused in a dying star. The aluminum in the frame was built by nuclear reactions in massive stellar cores. The copper wiring in your walls was assembled, atom by atom, in the extreme environments of stellar death. The phosphorus in your DNA, without which the genetic code of every living thing on Earth would be impossible, was produced in the last desperate burning stages of a massive star, and flung into space when that star exploded. You are not just in the universe. You are of the universe. You are the universe experiencing itself. And every atom in your body is a testament to the violence, the beauty, and the sheer creative power of the cosmos. From the simplest hydrogen, born in the first seconds of time, to the heaviest elements, forged in the final moments of dying stars and the collisions of their remnants. The periodic table is the autobiography of the universe. It tells the story of how simple became complex, how chaos became chemistry, and how the raw material of a young and featureless cosmos was gradually transformed over 13.8 billion years into a world rich enough to produce consciousness, curiosity, and wonder. We live in an extraordinary time. We are the first generation of humans to understand, in broad strokes, where the elements come from. For most of human history, the origin of matter was a mystery. The ancient Greeks thought the world was made of 4 elements: earth, air, fire, and water. The alchemists spent centuries trying to turn lead into gold, never realizing that such transformations do happen in the universe, just not in any laboratory they could build. They searched for the Philosopher's Stone, not knowing that the true Philosopher's Stone was a neutron star. And the transmutation they dreamed of required conditions that would vaporize not just their laboratories, but the entire planet. It took the combined efforts of astronomers, nuclear physicists, chemists, and astrophysicists over the past century to finally piece together the true story. Hoyle's audacious predictions, Fowler's meticulous measurements, the Burbage's tireless observations, Gamo's wit and Alpher's diligence, Merrill's sharp eyes at the spectrograph, Kashiba's patience in the Kamioka mine. The LIGO team's decades of engineering, thousands of scientists, across generations and continents, each contributing a piece to the puzzle. And what a story it turned out to be. Not a story of simplicity, but of staggering complexity. Not a story of one process, but of many, each operating on different scales and different timelines. Not a story confined to one place, but one that spans the entire observable universe and the entirety of cosmic time. And it is not finished. New stars are forming right now, fusing hydrogen into helium, slowly building up the next generation of heavier elements. Massive stars are burning through their fuel at reckless speeds, building iron cores that will one day collapse and scatter their contents into space. Somewhere in the universe, at this very moment, two neutron stars are spiraling toward each other, destined to collide and flood a tiny corner of the cosmos with newly minted gold, platinum, and uranium. Somewhere else, an AGB star is patiently dredging up S-process elements from its deep interior and puffing them gently into the void. And somewhere, high-energy cosmic rays are slamming into interstellar atoms, shattering them into lithium, beryllium, and boron. The universe is still making elements. The periodic table is still being written. And in some distant future, the atoms forged in today's stellar furnaces will find themselves incorporated into new worlds, new oceans, perhaps even new life. The carbon being fused in a red giant right now may one day form the backbone of a molecule of DNA on a planet we will never see. The gold being minted in a neutron star merger at the edge of the observable universe may one day adorn the finger of a being who will look up at their own night sky and wonder, as we do, where it all came from. The cycle continues. It has continued for 13.8 billion years, and it will continue for trillions more, until the last star burns out and the universe grows cold and dark. But even then, the atoms will remain, changed, scattered, perhaps frozen in the depths of dying galaxies, but still carrying within their nuclei the memory of the fires that forged them. But for now, the stars are still shining, and the elements are still being made. And you are made of all of them. If you enjoyed this journey through the cosmic history of the elements, please consider hitting that like button and subscribing to the channel. Leave a comment telling us which element's origin story surprised you the most. Was it the gold from neutron star collisions, the carbon from the triple alpha miracle, or maybe the lithium from cosmic ray bombardment? We would love to hear from you. Thanks for watching, and we will see you next time.